Okay, I think we're ready. Uh, we are getting close to wrapping up. We've got a few topics, like 3 topics. Well, one of them's divided into a couple of subtopics, but not that many topics left until we are finished with the core content for this course. We're moving on to torsion now. So first bit of the exam 1 was axial type forces. Exam 2 was mostly flexural type forces. Exam 3 is actually a combination of everything, but the new thing in Exam 3, one of the new things, is torsion. So those are the 3, axial, flexural, and torsion are the 3 types of forces that might create stresses and strains in some kind of object that you're dealing with. And so we're finally at the end of them. This course doesn't combine them all together into one object that's being stretched, flexed, and twisted at the same time. That'll be a follow-on course if you need that. So we do keep them separate in this course. But the one for now is torsion. So let's look at what we've got for torsion. We're going to introduce it. Today's probably a shorter day because we're going to break it into a couple of sections, the torsional sections, into a couple of pieces. I think we'll introduce today, and then we'll probably work through a problem, maybe 2 problems, and call it good for today. So shouldn't be too long. I'll look at the chat and make sure there's no questions in there that we need to answer. But let's look at. Oh, you know what? Hold on. I've got to reset the screen. I didn't think about that. If I don't do that, then it's going to make it hard to draw on the screen. So I need to reset it. Although I'm not sure what. There it goes. Dun, dun. Okay, that should. There we go. All right. Now, back to our torsion. So torsion is twisting, and you can even hear the word torque inside torsion. Remember, it's been a month or more now, but when we first introduced moments, we were talking about summation of moments and things like that. I probably mentioned something that in maybe just a pure physics type class, we don't use the word moment, we just use the word torque for all kinds of forces at a distance, applied at a distance. Here we are actually going to talk about torques. And so in engineering, torques and moments, they're the same thing. We just use the names to mean kind of different applications. So we reserve torque for usually we're talking about some kind of twisting motion or sense about a shaft. So a shaft is being torqued or it's delivering torque or something like that. Maybe in an engine or a drivetrain or an axle or something like that. And we use moment for we've got a force applied at some distance that's making something wanting to twist. It's all the same thing, but we do keep kind of the names torque and moment have a little bit different meanings, even though they're really the same thing. So in our, let me think. Yes, in our course, our torques are going to be applied to shafts. And the shafts that we're going to use are going to be round. So we're not going to have some hexagonal shaped shaft or a square shaft or triangular shaft or anything like that. Although you could, and there might be a reason for you to. But in here, we're just going to do round, so circles. Now, they could be solid shafts, a solid rod, or they could be hollow in like a tube. But either way, they're going to be round circular cross sections. That is it makes one part of what we're doing simpler, maybe actually 2 parts simpler, because if you have a faceted shaft, so like a hexagon or a triangle or something like that, then those corners create some extra stress concentrations that we aren't accounting for. How much of exam 1 and 2 will be on the final? That's a decent question. So we haven't really got there yet, but the final is comprehensive, and I would say it's not like a third, but it's similar to that. It's not exactly that anyway, but it's similar to that. So a third of the questions, more or less, on exam 3 come from exam 1 content, the axial stuff. another third come from the flexural stuff from exam 2, and the last third come from the new things. So it's somewhere in that range. It's about evenly divided. So the stuff we're covering now is probably represents somewhere around a third of the points on exam 3. I don't know, you know, those aren't exact numbers, but somewhere in that range is about how it gets divided up. Because there aren't that many new topics that we're introducing. We've got, I think, maybe 4 or 5 lectures, and maybe not even that many, and that's the new stuff. And 2 or 3 of those are just torsion. So, since we're stuck with torsion on round circular shafts, let me draw a kind of generic diagram that labels all of our new variables. Because we have some new variables that we haven't used, or maybe we've used them in different ways. So this is going to be actually let's make it more of a oval. And we'll put this one here, we'll copy it and put one, I don't know, somewhere up there. And then we'll connect it together. And you know, this will be in the background back there. All right, so there's our little shaft that we're dealing with. It looks a little bit misshapen there. I wonder if I can, there we go. That looks better. There we go. Hold up. I want to get it maybe like that. All right, so one variable is just going to be the length. So that one's not anything particularly new, because some of the things that we're going to do have to deal with the length of this thing will determine how much it might twist. So a longer tube is going to twist more given the same amount of torque than a shorter tube with that same amount of torque. And so the length is one variable that might matter. Obviously the torque, so now I'll have to put an opposing torque or else it would be rotating. We do have one category of things we're going to talk about called power transmission, where the shaft is spinning and it's transmitting power. But in general, we're thinking of these things being in static equilibrium. Even the spinning shaft isn't actually going, it's not translating, it's not going anywhere, but it is spinning in place. So in that case, the torques would, there would be a torque that caused it to spin. L, I guess I didn't write it down, but that's the length. We have, now I drew this one as a solid or maybe a really thin tube, but let's draw a inner diameter here. Because it could be hollow. I'm not going to draw the hollow hidden lines. In fact, maybe I'll just erase these to make it not so confusing. There we go. So it could be that our shaft that we're dealing with is a tube. And in that case, we have a inner radius. And we're going to call the inner radius, we're going to call that B. And we have the outer radius. We're going to call that one C. And if we have a solid shaft, then B just equals 0 in any equations that we might use. So that's how we'll deal with a solid one. We'll just make the inner radius 0 if it ends up that it's a solid shaft. Let's see. I think we could get started. There is one other variable, but I don't know if I want to label it on here. We're not going to talk about it today, but basically it would be the angle of twist. So if we apply a torque to this thing and hold the other end stationary, or apply the opposing torque, then how much did it twist? So that is a thing that we will eventually talk about, but I don't think we'll talk about today. Maybe, I just don't know. it would kind of clutter up this diagram to put it on there. All right, so given this, the equation that we're mainly interested in is if you were to twist this thing, how is it going to fail? And in this case, there's two failure ways. One of them is it twists too far, so that's the angle of twist that we probably won't talk about today. The other one is it yields or fractures. So it's kind of like the axial stress where you pull too hard and you break the part in half. Here, you twist too hard and you twist it in half. Or you twist it and it yields, it permanently deforms, and then that's probably also failed. So that equation, if we think about how that would fit into our sets of equations, we have the axial stress stuff where there was a force and it was applied perpendicular to an area, and it would, stretch or compress. And there were the shear stresses where there was a force and it was applied parallel to an area and it would try to shear or slide that surface past the mating surface, I guess. So this is more like the shear, where we don't have a force, we have a torque created by a force somewhere. Normally we don't see the force that creates the torque, normally we just see the torque. But we have this torque, and we're thinking that this torque might cause a failure, and that failure would be on a cross-section that is not perpendicular to the torque. We're going to imagine it as kind of like parallel to the torque, but really in reality it's kind of at a 45-degree angle. That's not important for what we're doing. So we derive a shear stress equation. And if we were to do that, we would end up with a tau, because that's a shear. In this case, it's going to be a torsional shear stress. And torsional because it's coming from a torque. And the equation for this is going to be the torque. So here I've shown an external torque. The red arrow, curved arrows, those are external torques. This torque in the equation is just like the forces that go into our stress equations for axial stress or flexural stress or any of those other stresses. That's the internal torque. So we do have to make sure that we're using the internal torque. And then T times, I guess there is one other variable that I didn't put out here, rho over something called J. So rho is also, it's related to B and C, but it's just some distance. So rho equals the radial distance from the center. So it could be B if we were measuring from the center to the inner surface of the hollow tube. It could be C if we were measuring from the center of the rod all the way to the outer surface of the rod. Then it could be C, but it could be any number from 0, the center, out to the surface C. So any number in between there. So it's just a variable. J is a new thing. J is called the polar moment of inertia. So it's like I, the moment of inertia, that we have been using in the flexural stress equations. But since we are dealing with a shaft with a torque that's about the longitudinal axis of the shaft. So if I had drawn, I didn't draw one, but if I drew a, let's make it blue, I guess. If I drew a longitudinal axis here, then the torque is about that axis. Whoops. And so polar moment of inertia is related to similar concept as I, moment of inertia, but in polar coordinates. And so the actual equation is the integral of rho squared dA. Rho is the same thing as it was, we just talked about, that radial distance. We are going to only use circular shafts, and this is where things would diverge if we were not using circular shafts. So instead of having to integrate rho squared dA for every cross section, since we're only using circular cross sections, we can just evaluate rho squared dA, integral of rho squared dA, as pi over 2 times c to the fourth minus b to the fourth. So c and b are those outer and inner radius numbers. I guess if you wanted to use diameters, because sometimes diameters are easier to measure and know, so it would also equal pi over 32 times the outer diameter to the fourth minus the inner diameter to the fourth. So either of those equations work, but only for circular cross sections. So if you do have a shaft that's a hexagon shape, then you'd have to go and find the polar moment of inertia for a hexagon. So these pi over 2 or pi over 32 equations, those are only for circles. It doesn't matter if they're hollow or solid, because you could, if they're solid, you could just make the ID, the inner diameter, equal to 0, or you can make the inner radius, b, equal to 0. So you can use these for hollow or solid. Okay, so that's all we need. T, we had to figure out the internal torque. Rho, we got to figure out where do we want to know this stress. So I will say this. Let's do this. So normally you want to do tau max, because you're most of the time interested in the maximum torsional shear stress. Not all the time, but normally you do want to do that. And tau max, if you look at the equation, T and J won't change. But if I want the largest value I can calculate, I'm going to put C in here, the outer radius. So a lot of times we're using TC over J because we want to find the maximum shear stress. But there might be instances in particular when you want to find the shear stress on the inner surface, like of a hollow pipe that's pressed onto some other shaft and they have to stay connected. You might want to know the shear stress between those two things to see if they're going to slip or not. So there are reasons you might do something other than TC over J. Why don't we do some simple calculations and see how this works. So let's look in web work and see if I can find a problem we can work on related to this. I don't think I've opened up the SA3 or the optional 3 yet, but I think I can look at them. Let's see. We could do that. Let's see if there's something a little more interesting than that one. That one's just solving torques, but it's a good starting point. But let's see if there's something more interesting. That actually looks, yeah, that looks like it'll accomplish the same thing as this one, but let us do some tau equations. All right, so, well, we don't need that. That was really loud. I don't know if maybe it wasn't for you, but it was loud for me. All right, so here's our problem. We've got some kind of electric motor. It's connected through this coupler to a shaft that has 3 different gears, C, D, and E on it. And the motor is supplying 550 Newton meters of torque, and then it gives us a diameter for the shaft, and then it talks about these torques removed at gears C, D, and E. So what's going on here is whatever, there's a gear at C or a sprocket, I don't know, well, it says gear, so gear at C, and it's connected to some other stuff we're not seeing. So maybe, you know, maybe there's some gear over here that is running some other piece of machinery, and that torque transfer requires some known amount of torque. So that's what it's saying. So if we draw kind of our free body diagram of this thing, it would look something like this. I'm going to just draw the shaft. Maybe I'll draw the gears at C, D, and E, or some boxes for those so that we kind of know where they're at. But let's draw our free body diagram of this thing. So here, that's the shaft that's running through the center of all this thing. And we have an input torque of, for me, it was 550 Newton meters. So I'm going to draw this as a straight down arrow, but, you know, like I did up here. These are really torque, so normally they're curved arrows, but, and I guess I could try drawing a curved, I could do it that way. We'll do it that way, but, you know, you just have to bear with my curved arrows. What was it, 504? No, 550. This is another one of those that I don't know which way to draw this arrow. There's no real information about the motor spinning clockwise or counterclockwise. I don't know. So I just picked one direction for the input. So this 550 is the input torque from the electric motor into this shaft with all the gears on it. These pieces here and here, these are bearing blocks, and we're assuming are frictionless. So they're like a roller bearing or a journal bearing or something. I don't know. It doesn't. Well, this one actually, this one right here, the first one does show roller bearing elements in there. It shows like kind of like a little cross section. If you're not sure what those are, let me. You know, one of these kind of things, kind of like here. It may not be this particular kind, but something like this. There's some rolling elements in there, and there's an inner race and outer race. What the purpose of that guy is to keep the shaft in place, but let it spin relatively freely. So we're assuming it's perfectly freely, it's frictionless, but in reality, they do absorb some of the torque, some of the power that goes into your shaft, but we're assuming they don't. All right, so at C, I've got a gear. I'll put it kind of right here. We don't have to draw the gear, but I did. So here, this is, if I have the input torque kind of going whatever way you want to interpret that arrow going, then down, then here, this output torque is going to be the opposite of that, because, well, this is out of our system going off to some other thing. So whether you label it in or out doesn't typically matter. The important part is that I've got the 550 going into the shaft one direction, and the C, D, and E gears are delivering that torque outside of our system in the opposite direction. And it told me that it was 107 Newton meters. And then I'll have the same thing for each of these others, just different torques. I don't have to have different torques, but they don't have to be the same either. And then let's do the last one. All right, so we have some torque going out there, some torque going out there. And for me, the numbers are 150 and 293. And hopefully, if I get my calculator, those numbers should all add to 0. So I've got 550 going one direction, in to the shaft. And then I have 107 leaving, I have 150 leaving, and I have 293 leaving. And that, if you add all those numbers, they add to 0. 550 minus 107 minus 150 minus 293 is 0. And that's the way that these problems are going to work for us as far as the torque balance. This particular problem doesn't ask me to draw a torque diagram, but if I were, it does ask me in a roundabout way to do that, though. It does say tell me the torque in these different sections, BC, CD, DE, which would generate a torque diagram. But let's draw a torque diagram just so you kind of know what it means. So here is our reference axis, and we'll say that here we've got our torque measured in Newton meters, and the input torque is 550. So let's say that that is counted by 200. So 2, 4, 5, 50s, kind of right there. And there's no change in our torque until we get to that first gear C. And I've got 550 and I gave it a positive sign. So this direction arrow, the 107, is minus. So I would drop down to 393. So that would be kind of right in there. And then it would go over to here, and it dropped down by another 150, which should get me to the... Uh-oh. Did I... 443 here, not 393. Then this 443 drops down to 293, which... oh, well, 443 is actually up higher, isn't it? It's closer to right there. And drops down to 293, which is, yeah, we'll put it there. And then this one goes to 0. So it's sort of like a shear diagram. So if I wanted to know the torque in any one of these sections, then I could just look at a torque diagram like this, or I could, if I wasn't sure, I could, you know, cut the shaft open. So if we look at our lettering, this is point B, C, D, E, and I guess this would be F out at the end. It just doesn't tell me anything about it. So if I wanted to know the torque in BC, I could cut, that's a little green squiggly line, between letter or point B and C, draw that free body diagram, which would be something like this. Notice that there is 550 Newton meters in. For this section to be in equilibrium, then, well, I've got to have 550 Newton meters to balance it out. So the torque in section BC is 550 Newton meters. And that's also what my torque diagram shows. This is point B, there's C, there's D, there's E, and I guess F would be somewhere out there. I saw a question. Let's see. Why do the ones on the shaft all turn in the same direction? Is it? Oh, yes. So, yeah, that's an assumption we're making, is that in this picture, anyway, gear C, gear D, and gear E are all firmly attached to shaft, the pink shaft. So they're all firmly attached to the pink shaft here, and so they all turn at the same speed, but they don't all deliver the same torque. So the torque is determined by what they're connected to. So gear C only has to deliver 107 Newton meters. That's because whatever it's connected to is only using that much torque. But the last one, gear E, whatever it's turning needs 293 Newton meters of torque. So it's much harder to turn for whatever reason. And so there's more torque being delivered at E. But they're all delivered at the same speed because they're all connected to the shaft, you know, rigidly. So that's why they're all turning together. They're all turning at the same speed, but they might deliver different amounts of torque depending on what they're connected to. And when you add them all up, 107, 150, 293, those add to the total amount into the shaft. This 550 is coming out of the electric motor into the shaft, and then it's getting divvied up to the different C, D, and E elements, whatever they are. We should be able to go answer. The torque here should be 550 Newton meters. The torque in section CD looks like it's 443 R. If we didn't want to draw that, we could, cut between C and D and draw the free body diagram for that, which would look something like this. But it does have a gear C somewhere over here. And I've got the 550 in, and I've got the 107 out, and then that leaves 550 minus 107 is 443 Newton meters in that section. What is the difference between B and A? Why does A not count as a torque? Let me see. Well, it does. The difference between A and B is just in our picture, we've got this coupler here, and so it's just trying to give you a realistic type, like how would this really be built in the real world, sort of thing. So the section from A to B, it's like, I don't have an example here of anything that I can show you really quickly, but what is at A and B is something like this. Let me see if I can find a something to show you what it looks like. This. Whoops. So this little plate right here, well, that zoomed in. This little plate right here is 1/2 of what they're showing here at between A and B. You can kind of see those little bolts holding it together. So all they're showing, that it's not delivering torque outside of the system. It's just a way to connect, and maybe I should do it this way, a way to connect the pink shaft to the green output motor or output shaft of the motor. So that's all it is. And so what we're assuming is that there's no torque loss there. So if I were to draw the torque in section AB, it would just be whatever torque's coming out of the motor. So it would be the 550 Newton meters. So that's what AB is something like this, bolting the green shaft to the pink shaft is what it's doing. Hopefully that makes sense. Let's see, 443. Oh, wait, we're going back to here. We should have 443 here. And then in section DE, we have 293R. We could go in, cut this guy open, draw the free body diagram, and it would look something like this. And I would have I'd have two, that gear plus the gear at D, which maybe is over here. Do this. Let's see, this was 150. And so that would leave us with the 293. In each one of these free body diagrams, I'm writing basically summation of torques equals 0, which we've done before. We just called it summation of moments. And so that's what I'm writing in each one of these equations here. I just didn't write it out. So 293 for the last one. So those should all be correct, hopefully. Yes. All right. So now it starts asking me. Well, first it asks, last rather, it asks me location of maximum stress. So this is our torsional shear stress. This equation. So the maximum shear stress we always decided was on the surface. And J is the polar moment of inertia, which is the related to the cross-sectional area. Here, our problem says that we have a 35 millimeter diameter shaft. It doesn't mention inner radius or inner diameter or hollow or tube or anything like that. So this makes me think it's a solid shaft. So the location of the maximum stress, actually I don't know what it wants me to put it. Oh, enter BC, CD, or DE. So where's the highest torque in any of these sections, and that's going to be the highest stress. Well, if I go to my torque diagram, the highest torque was in section BC, 550 Newton meters. So I would put BC here, and that should be correct. Now it asks me for, well, what is the maximum shear stress? All right. We take our shear stress equation, T rho over J, except we want the maximum, so TC over J. And we put in our maximum values here. So T, the maximum value is 550 Newton meters. C is the outer radius. They gave me a diameter, I'm pretty sure. Yeah, 35 millimeter diameter. That's pretty common when you're talking about shafts and tubes and all that, is that you don't normally talk about the radius, because if you were to measure it, you'd measure the diameter. So normally you talk about the diameter. So we do have to make sure that we're using the right thing in our equation. Our equation wants a radius. So 35 millimeter diameter would be 0.035 meters, but we want it divided by 2 because we want the radius. And then J is pi over, and we get to decide here, do we want to use the pi over 2 with the radius numbers, or do we want to use pi over 32 with the diameter numbers? I'm going to use the 32 since we were given a diameter. Pi over 32. This is a solid shaft, so I don't even, the inner diameter is 0. I don't even need that part. So the outer diameter is the 35 millimeters. I am going to convert it to meters and then raise it to the 4th power. I need to make sure that's not 0.035 meters to the 4th. It's, that number raised to the 4th. So I probably should put the 4th outside the parentheses, but I just did it that way. So 0.035 raised to the 4th times pi divided by 32 gives me my denominator. 550 times 0.035 divided by 2 divided by my denominator is a big number, 65332 408.13. These units would be, if I worked them out, newtons per meter squared, which is a Pascal. Normally Pascals are really small, so normally I'm talking about mega or gigapascals. It looks like this would be 65.33 megapascals. Let's see if it wants megapascals. So 65.33, and we've got it all correct. So that's kind of the basics of how these problems work. They don't get a whole lot more complicated, but like things that could complicate them are maybe the shaft steps down, changes sizes, and so you have different diameters or radius numbers. Maybe it's hollow somewhere and solid in another place. Maybe you're trying to solve for the shaft diameter. So there's different ways to approach the problem to make it simpler or more straightforward, or more complex. Let's see if we can find another web work that would make sense for us to work on right now. This one does ask about angle of twist. We haven't covered that yet. This one is basically just what we did, so that's not anything new. It's just adding angle of twist. This one's, let's do this one. We just won't do the angle of twist part. We'll save that for tomorrow. Yeah, tomorrow. There we go. All right, so we've got this shaft consists of a cold rolled bronze hollow tube. All right, so I've lost my pen. Where to put it? I don't know where I set it down at. Here it is. All right, so we'll color that yellow. So this part is hollow, and it's one material, cold rolled bronze. It's securely connected to a cold rolled stainless steel rod BC. So we'll make that one green just to have a different color there. So that's a different material. And then we have some dimensions. Tube AB has an outer and inside diameter. Rod BC has a diameter of 3.6. We've got some torques. And we have some links. We don't need the links right now because we're not doing angle of twist. So we want to find the shear stress in both sections. So in the bronze section and the stainless steel section. So pretty straightforward. I think I'll draw this one sideways, side view, so we can see it a little better. The 3D might be confusing. The material matters, bronze and stainless steel, that matters when we do the angle of twist. But for the shear stress, it doesn't matter for the stress calculations. It would matter for like factor of safety though. So here's a side view of what we've got. We're going to draw this as like connected to a wall. And then we will put the yellow section, I'll draw it a little bigger just to have room to label stuff. Now it is hollow though, so we'll put a dashed line to show that it's hollow. And we'll have another one. Something that the bottom one's better than the top one, but it's fine. And then we have the solid green section. Let's see, the inner diameter is 2.5, so it's a little bit bigger than that. We'll draw it like this. And L1 and L2 are close to the same numbers. We'll do it like that. Okay. Let's put our dimensions on here. You don't have to draw these free body diagrams, particularly on an exam. I'm just drawing them so that you're better able to understand them, but they're pretty straightforward. Now, if you're confused on internal torques, then yeah, draw the things. You don't have to be very fancy drawing them, just draw them to understand. L1 is 2.2 feet, and this one is 2.8 feet. And then I'm going to draw our torques as arrows. So I'll draw this one kind of going up here. It says T2 is, and maybe you don't want to draw a straight line. I did, but it might make you think it's a point load. So we'll draw this curved, 45 kip inches. And this one is shown going the other way, and it's 95 kip inches. Now, this is not a free body diagram, right? What I've drawn, because it's connected to the wall. So technically, to draw a free body diagram, I don't need this, right? But I need to replace that connection with some kind of stabilizing torque. So I really need enough torque going that way up, you know, if you want to call that up, to balance the 95 going down. So I need another 40 kip inches so that my 40 plus 45 going up equals the 95 going down, and it's in equilibrium again. Oh, actually not, no, that would be 50, not 40. Okay. Let's see. Let's do our diameters. So we've got this guy, the first one, or well, actually I think this is section 2, has a solid diameter. Notice it calls it a rod. That means it's solid. 3.6 inches. And then the tube means it's hollow. And I've got a outer, I think it gives me diameter of 4.9 inches. And then I guess I'll draw the inner one kind of like this. Normally you don't draw diameter dimensions the way I'm doing it, but it's okay for what we're doing. 2.55. Okay. Now we need the shear stress in, I assume it means the maximum shear stress in both sections of the shaft. So let's do the solid, the yellow, the green part first. So here I've cut in the middle of the green section. You know, maybe I should, you know, this is green from our previous diagram. And here's our yellow from our previous diagram. So in the green section, I've cut through the middle of it, and I can draw either free body diagram, you know, the left side or the right side. Looks like the right side's easier to do. So, whoops, we would have something like this. And it looks like there's a 45 kip inch going there, and I'd need a balancing one to make it equal to 0 of 45 kip inches. So the green section internal torque is 45 kip inches, and it's going down. Notice most of the time you don't have like plus and minus values for shear stress, because it doesn't really matter if you shear like one direction or the other direction. It's really the same effect on the material. Just noticed my camera is froze, so you didn't see me do any of that. So let me unfreeze. So what I did was, it doesn't matter if you shear this way or if you shear this way, the effect is the same. Sometimes, you know, forces and stresses are different if they are in tension or compression, but shear isn't really a tension or compression thing. It's just sliding layers sliding past one another, and so we're not worried about plus shear stress or negative shear stress. You just need to make sure that you have one mentally assigned. One of these directions is a positive shear torque, and the other is a negative torque. There is a right hand rule that you can use if you have an axis. So like an axis here, then the torque that makes it, your fingers on your right hand curl around your axis, that's the positive direction, or if it goes the other way, then that's the negative direction. But in general, we're not going to worry about positive and negative torques because it's a little bit confusing for where we're at right now. Just know that you have to assign the 50 and the 45 on our picture here the same sign, and it has to be opposite of whatever you assign the 95. So that's the only thing we have to keep track of. All right, so I've got to find tau for, this is, well, it's not even labeled. Oh, BC. I see some letters on our diagram here, A, B, and C, so this is section BC. Stress in BC is equal to the torque in BC times the outer, we want the worst case, so the outer radius of section BC over the polar moment of inertia of section BC. So the torque we just found, 45 kip inches. Remember that kip means 1,000 pounds, so this is 45,000 inch-pounds. C is the radius, so it's going to be the 3.6 inches, but that's a diameter, so divide by 2. J, it's a solid rod, so that's the pi over 32 times outer diameter to the 4th. So if we do all this, 3.6 to the 4th times pi divided by 32, 45,000 times 3.6 divided by 2 divided by denominator, 4,912.19. The units here would be pounds per square inch, so that's PSI. So 4.9 KSI. It does want it in KSI, so 4.912. And let's see if it likes that. And it did. Okay. The yellow section, I need to, cut through the middle of the yellow section. I can draw the left-hand side or the right-hand side. In this case, looks like drawing the left-hand side is simpler. So that would be something like this. We don't have to be super fancy with it. I'm probably drawing too many hidden lines. We have the 50 kip inches. Now this one is not given to us on our diagram. It's just shown that it's connected to the wall over here. But when I drew my free body diagram, I disconnected this set of shafts from the wall, and I had to replace the wall with what the wall was doing. So I made the whole thing in equilibrium, which meant there had to be 50 kip inches going, what I've shown as up, to balance out all of the torques here. If there were forces, now there won't be, but if there were forces like point loads, that doesn't affect this. We're not combining flexural things with the torsional things. So these are, even though they're drawn crooked, so they're not straight like a point load would be, but these are torques that I'm balancing. So the internal torque here looks like, which way I've been drawing those like this, needs to be 50 kip inches. And it needs to go in the, downward looking direction here. Now I did draw these from the different directions. I drew the green one from the free end inwards, and I drew the yellow one from the wall inwards, so they're drawn from different directions. If I were to draw the other half of this one, let me draw it real quick. I would not normally draw both of these, but just to show you what's going to happen. So there's the 45. There's the 95. And for this one to balance, I need the 50 kips to go up again. So it does matter when you're drawing your free body, if you're drawing the free body diagrams, to figure out the internal torque, and you're trying to keep track of, is this internal torque up or down? It does matter which direction you drew the free body diagram from. So drawing from the left hand side inwards, made it look like the 50 kips is going down. Drawing from the right hand side inwards made it look like the 50 kip inches is going up. So if you're, for instance, trying to calculate angle of twist, which we'll do later, you need to know, is that section twisting this way or is it twisting the other way? And you can tell by the internal torques, but you have to draw all of those free body diagrams from the same perspective or mentally flip them around in your head. If I look at the two of these that are from the same perspective, so those two, then the internal torques on the green section, so this one, internal torque there is going down. Internal torque on the yellow section is going up. So they're actually twisting in opposite directions. As far as shear stress goes, same magnitude of shear stress, but direction of twist, which way is it twisting, is actually different in these two. So part of this is weird to think about, but the yellow section is twisting one way and the green section is twisting the opposite direction. And together, maybe they don't twist at all. We'd have to add them up and calculate them to see, what the overall effect is. And we'll do that tomorrow. But let's go ahead and calculate our shear stress. Tau in this section AB is the internal torque in AB, the outer radius of AB, and the polar moment of inertia for AB. So this will be, the torque is going to be 50 kip inches, and technically it has the opposite sense from BC. I gave BC a positive sense, so technically this has negative, but for shear stress, we don't care about positive and negative. The outer radius of AB, I've forgotten, 4.9 inches is the diameter. And then the polar moment of inertia, this one is hollow. So pi, I'll do the diameter version again, 32. Outer diameter to the fourth, so 4.9 to the fourth, minus inner diameter, 2.55. So something like that. So a more complicated equation to solve, but we should be okay. 4.9 to the fourth minus 2.55 to the fourth times pi divided by 32. 50,000 times 4.9 divided by 2 divided by the denominator. 23 35.79 psi. So let's see, does that make sense? Generally, let's see if it's the right answer. 2.33, 2.33, yes, looks like it is. 579. And it's correct. The bottom one here is an angle of twist. We haven't talked about that yet, so we haven't gotten there yet. So those are pretty much the types of questions you'll answer with the torsional shear stress. You might work one of them in reverse, I suppose. I didn't see one of these that worked in reverse. That's the one we just did, isn't it? No. So this is slightly different than the one we just did, other than the fact that gear B is drawn bigger than these others. This one's working backwards to figure out, well, if I know all the torques in here, then how big does the shaft need to be to maintain some factor of safety? I think we'll work this one tomorrow when we also can do the angle of twist. And so this will we'll save it for tomorrow. We'll do the diameter calculation and the angle of twist calculation on this one together, along with some other angle of twist problems. So that's pretty straightforward. not a lot of new equations. You've got one equation to, well, two technically, I guess, because you do have to remember polar moment of an inertia equation, but you have your torsional shear stress equation you need to remember, and then the polar moment of inertia. So it's pretty straightforward. And most of the topics from here on out, actually probably all of the topics from here on out, are this level of stuff. So they're not quite as in-depth as trying to figure out every member force in a truss, or the pin reactions on a frame or machine. So it's a little bit simpler topics. I think if you've made it through exam 1 and 2, I think you'll find this stuff kind of a little more relaxing than those topics were. I believe I've opened up homework 18, which begins some of this. You may not can do all of it because some of it is angle of twist, but you could start on it. And we'll be back tomorrow with another, again, pretty short lecture on this same idea, but with angle of twist. So I will see y'all then. Let's see, yeah, no new questions in the chat. So I'll see y'all tomorrow at noon, and we'll do a little bit more of this in the concept of angle of twist.